say something about, because I realized talking to some people that this is something that maybe I haven't explicitly said, and it might be helpful to say this. In terms of my expectations for the modules. So my expectation is that you will need to revise them. So if you turn in a module and I send it back to you and I say, good work so far, but here's some things you have to fix, right? That's evidence that this is going exactly how it should go. This is not evidence that like, you're stupid or you're not figuring it out or whatever. Like, I think out of all the people who have turned in modules, like, there's probably like 100 things that individual people have turned in so far. Maybe there's like one or two where people have gotten credit the first time. So that's just to say, like, that's the expectation, that's normal. And sometimes, like, there's people that have even like had to revise things multiple times, like 3 or 4 or 5. I mean, I think last time I taught this, the record was like, maybe there was like 8 or 9 times, and hopefully that doesn't happen. If it's taking me that many times, then maybe come and meet with me and we can like work through it together rather than me like keep sending it back and forth. But that's to have to revise it even multiple times is pretty normal, and that's just I don't require perfection, but I have pretty high standards, and I want to make sure that you understand whatever the concept is, and so just putting some stuff that like looks similar to the right answer, like I want to make sure that you actually understand. So that's I just wanted to be clear with that, because I think and of course, right, it doesn't matter if you get everything right the first time or you have to revise it 5 times. When you get credit is credit. Like at the end of the day, it doesn't really matter if it took you a bunch of tries or you got it the first time. In some ways, maybe having to try a bunch of times is better, because you might end up learning actually more than if you just like did it right but then forgot about it or something. I don't know. Okay. Then also, so some of you, if you've looked at the module, whichever is the latest module, one of the things you're required to do to get credit is to fill out this survey. And if you haven't seen that, even if you've requested an extension on the module or whatever, do go and fill out the survey. It won't take you very long, and it's just a helpful way for you to get some feedback on like how you think the class is going. If you have suggestions for things that I could do that would help you learn better, or whatever. And I know some people have filled that out already, and that's been helpful. Like for example, I think there was someone that said, hey, can you make a way for that when you run Disco, you can find out what version it is, so that you know if you have the right version. It's like, oh, that's a good idea. So I've done that. It won't let me upload for some reason, so I'm trying to figure that out. But as soon as I can upload. But anyway, so what are we going to do today? I mean, there's other things I could tell you about Disco, and that was kind of what I was originally thinking, but thinking more about what people are struggling with on the modules and some of the feedback that I got, on the first few people that filled out the thing. I decided, I think what we really should do, I'm just going to spend today just doing a bunch of example proofs, because that seems to be the thing that a lot of people are struggling with, and that totally makes sense. That is like, you all know how to like solve algebra problems or like, do math problems of that sort, but like writing proofs is completely new probably for many of you. I thought it'd be helpful I'm just going to do a bunch of examples, and then you can have it, you can go back and rewatch it later, or you can PDF. I also wanted to mention, so this book, I think I listed it on the website as like an optional resource for you. I think a couple people have gotten it and found it very helpful, and I think this is a very good book. So especially if you feel like I'm struggling writing proofs, I would like some extra help, like figuring out how that works. This is a great book, it's only, I don't know, I think you can probably find a PDF of it somehow. You can like an ebook version. I think you can get a paper copy for only about $30 or something like that. So it's not ridiculously expensive. Definitely could be, again, it's not required, but it could be a good investment, especially if you feel like you want some extra extra help with that. And even if you feel like, let me say this. Most of you will probably not have to write formal proofs in like your future career, right? I mean, most people don't. I do, but I'm weird because like I'm an academic, so that's part of what I do. But if you become a software developer, no one's going to require you to write like formal proofs of things. Or if you go into data analytics, or like I don't know. There's just like you're not going to have to do this kind of thing. But being able to think carefully and logically and like reason about things, right? Which is really the skill that you're building here. That's super helpful. If you can take a problem and say, well, I can think logically about how to break this problem down, or at least convince myself informally that this thing I'm trying to do is correct, even if I'm not writing a formal proof. But it helps me think logically about what would be a way to convince myself that this algorithm I'm writing is correct, or that this way I'm thinking about this is correct. That there aren't any like weird cases I haven't missed, or so it's a even if you don't expect that you're ever going to write formal proofs per se, that's kind of why we're doing it, right? Is that it teaches you how to think more logically about problem solving. All right, so without further ado, well, just any questions about anything I've said so far? I'll get this done. Cool. So most of the examples that I kind of honestly I just flipped through like chapter 3 of the book is like proof techniques, which is we've talked about this, but it goes into way more detail in the book. And I just picked out some interesting examples that they do in the book. I'm going to do them. So if you get the book, you'll see the same examples in there, but often in even much more detail, like explaining exactly how you would go through thinking about doing it. So. So let's see, the first one is suppose A and B are real numbers, and A is greater than B. If AC is less than or equal to BC, then C is less than or equal to 0. And so in some ways this is a fairly simple statement. It's just about like things being greater or less than 0 or less than each other. It's a good example of the kind of thing where, I don't know, when I try to think about this like intuitively why this is true, my brain ends up getting a little tied in knots because somehow it seems just complex enough that I have a hard time wrapping my brain around why, like whether I believe this is true or not. But if we kind of can break it down step by step, we don't have to hold the whole thing in our heads. We can just try some things and go step by step and see what happens. So, formally, how would we write this in formal logic? Right, I would say something like this. So it's making a statement about all A and B that are real numbers, right? So it's something like for all A and for all B, which are real numbers. And it's saying suppose A is greater than B, so that's really like an if, right? It's saying if A is greater than B. And we could write this as I guess we could write this as an and, right? We're supposing A is greater than B and AC is less than or equal to BC, then C is less than or equal to B. There's different ways you could write this, but okay. So I look at this and I say, all right, it's a for all statement. So I'm gonna be proving this about arbitrary A and B, right? So I can start by saying let A and B be arbitrary real numbers. one of the things that I like about this book, that I don't really, I feel like if I went through this, it would kind of be too much detail, or it would take us too long. I'm just going to like write out a paragraph, like you would see a normal proof written, but I like the book that it kind of walks through thinking of proofs in a more structured way. So it with indented things, and like, okay, suppose this, and then indented inside of that, now you have to prove this thing. And then maybe, it says, okay, now suppose this, and indented inside of that. So it's kind of like, almost like writing a program where you have, stuff indented inside of other things. It helps you kind of see more of the structure of how the proof works, as opposed to just being like a bunch of text in the paragraph. Okay, well, now we have to, and we're going to suppose, because we're trying to prove an if, right? So we said, suppose they're arbitrary things. Now we said, if this stuff, then this. Okay, so actually, let's stop here for a second. Because one thing we could do is just say, suppose this stuff, then we have to show that C is less than or equal to 0. But just intuitively to me, like, it's not clear how we would do that, or it seems like it might be more useful to do the contrapositive, where we say, suppose this is false, then we have to show not this. Why do I say that? I don't know. I mean, we can do it either way. If we start here, we say, suppose all this stuff, how do I show that C is less than or equal to 0? And I stared at it like, I don't know. Well, let's try the other way. Maybe that will be easy. So we'll do a proof by contrapositive. So suppose not C is less than or equal to 0, that is, C is greater than 0, right? Then we must show not A is greater than B, and AC is less than or equal to BC. That is, what would this be? This would be A, so not A greater than B, which is A is less than or equal to B, or AC is greater than B. Does that make sense? I just use like the Morgan's law to distribute that not over that thing. Trying to think of the best way to proceed. I think I've already made this slightly more complicated than the way the book does it when I was looking at the example, but that's okay. Yeah, I think I'm wrong. That's okay. So, all right, how do we prove? So I suppose that C is greater than 0, and I have to prove this or. How do I do that? Well, one way I could do that, well, if I just like can see that one of them is true, then I could just say, well, that one is true, and that's fine. In this case, it's not immediately obvious that why either one of these would be true, right? I mean, if I'm assuming something about C, I can't really conclude anything about A and B necessarily. And same thing here, just knowing that C is greater than 0 doesn't immediately tell me something about this. However, one thing I can say is, well, I could think about two cases. I could do a proof by cases. Yeah, I was going to make a suggestion for something. Okay, go ahead. What's your suggestion?
If C is positive, it
so I think where we're going to go is say, well, maybe it's helpful to say, let's consider two cases. Either A is less than or equal to B, or A is greater than B. If A is less than or equal to B, then, well, this one is true, and that's fine. If A is greater than B, then we have to prove that this one is true. Right? But now we know that A is greater than B, and we know that C is greater than B. So, consider two cases. Either A is less than or equal to B, or A is greater than B. I could say if A is less than or equal to B, then clearly A is less than or equal to B, or AC is greater than BC, because, well, the left side is true, so otherwise, if A is greater than B, then, okay, well now, I can multiply both sides of this by C. Multiplying both sides by C gives AC is greater than BC. And the important point here is that because C is greater than 0, when you multiply both sides of an inequality by a positive number, it keeps the inequality the same. If you multiply both sides by a negative number, you have to flip the sign. I don't know if you remember this from probably algebra 2, you're supposed to learn this. But I'll say since C is greater than 0. That's why the C greater than 0 part is important. That's it. Basically that. Any questions about this one? It's actually, as I said, this one actually ended up being slightly more complicated than I was intending for our first example, but that's okay. We'll do other ones. Okay, how about if x squared plus y equals 13 and y is not equal to 4, then x is not equal to 3. Okay, formally, this is really a statement about, for all x, I guess it's about real numbers. If x squared plus y equals 13 and y is not equal to 4, then x is not equal to 3. So let's prove it. So let x and y be arbitrary real numbers. Okay, and now I have to prove this implies. There's a few different ways I could do this. One way I could do it is we could do something similar to what we did in the last one and use a proof by contrapositive and say, suppose x is equal to 3, then we have to show the negation of this. And that would work. You could do that, and you could organize it that way. I'm just for the sake of an example, I'm going to do this one a little bit differently, which kind of ends up being the same thing, really, but it's maybe a little different way to think about it. So we're going to do more of a direct proof. I'm just going to say, all right, let's suppose this, and then we have to show this. But then we'll use a proof by contradiction. We'll say, okay, well, I'm trying to show that x is not equal to 3. What if x was equal to 3? I'm going to show that that leads to a contradiction, therefore, actually it's not. Right? So, suppose x squared plus y equals 13, and it's a proof by contradiction. Remember, if you're trying to show P, you suppose not P, and then you show that that leads to something that's impossible. So then you say, well, turns out not P wasn't correct in the first place, so suppose x equals 3, right? That's the opposite of what I'm trying to prove. Well, now I've supposed that x squared plus y equals 13, and I've supposed y is not equal to 4. I also now am supposing that x equals 3. So I can put those together. Therefore, x squared plus y equals 13 implies, if I stick in x equals 3 here, I get 9 plus y equals 13, which implies that y equals 4. But I assume that y is not 4. Yeah, so I now know that y is 4, and I also know that y is not 4. Everything goes up, right? So, but this is a contradiction. Since we supposed y is not equal to 4. Therefore, in fact, x is not equal to 3. Right, because it was supposing x equals 3 that led to that contradiction. So that was actually wrong, and x is not 3. Questions about this one?
Matthew, so when using proof by contradiction, you don't actually have to negate the entire proposition.
You do. You negate the entire thing that you're trying to prove. So at this point in the proof, right, we suppose x and y are arbitrary, and now at this point we're trying to prove this implication. And then we said, well, we're going to do that by suppose this, then we have to prove this. Right, so at that point, I had all these things that I was assuming, and then the thing I was trying to prove is that x is not equal to 3. So I do negate that. I say, all right, let's do that by negating that and showing that leads to a contradiction. Does that answer your question? Yeah. I don't negate like the entire thing because I just negate whatever I'm trying to prove at the moment. Other questions? Mason, did you have a question? You look like you have a question.
I'm just like trying to read it back.
Okay. Let's see. Here's one. This one is, I think we've done part of this before. We've done something like it before, but it's worth doing it again. So, for any natural number n is even if and only if n squared is even. So this is for all natural numbers n, even n, if and only if even n squared. And recall also, even n is defined to be, there exists some natural number k such that n equals 2k. Just kind of an aside, like we've done this before multiple times, and we've talked about like on one of the modules you have to define what it means for n to be a square, and we've used this notation when we define what it means for n to be even. I mean, you wouldn't have to make up a predicate even, you know, you could just write like exists k blah 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 like right in here. But that gets a little confusing because you need to be careful with your parentheses and like there's multiple exists like nested inside of it. So it feels a little bit easier to read and easier to understand and easier to work with if we kind of split it up into some definitions. And we say, all right, well the top level thing is, you know, it's just some simple like this implies this or if only this, and I define some things, and then I can like break those definitions down further. But anyway, it's not like required, it's just helpful. Okay, so first of all, it's a for all, right? So I say, all right, let n be an arbitrary natural number. Okay, how do I prove an if and only if? Well, an if and only if really means, like P if and only if Q means P implies Q and Q implies P. And the way I prove an and is I have to prove both those things. So this is going to split into two subproofs. I have to prove that if n is even, then n squared is even, and I also have to prove if n squared is even, then n is even. I have those two things I have to prove. So I can write that out. We must prove both. Even n implies even n squared, and even n squared implies even n. So let's say even n implies even n squared. Okay, how do I do this? Well, this is an implication. So again, I could prove that kind of by direct proof. Suppose P, then prove Q, or I could do a proof by contrapositive. I think in this case, a direct proof is going to be the easiest. So suppose n is even. And this is the point at which I could say, okay, what does it mean for n to be even? Well, I look up here at my definition, and I say, oh, well, that means there exists some k. So I can say that is, there exists k such that n equals 2k. Okay, my goal now is to prove that n squared is even. So it's helpful to say this explicitly. Kind of at any point during the proof, you kind of implicitly in your head, and actually if you look at this book, the book actually like kind of shows you how to write it out explicitly. There's always kind of like, there's some things that you're currently assuming, or that you've been given, and then there's a thing, your current goal, like what are you trying to prove right now? And it's always like, either I can do something to, so for example, if my current goal is to prove P implies Q, one thing I could do is to say, well, I'm going to say, all right, let's suppose P, so that kind of moves over to the column of things that I'm given, and then now my goal has changed, now my goal is to prove Q. But your job is always like to use the things you've been given to prove the thing you're trying to prove, and you kind of have to keep track of what these things are. So we're just kind of doing it in our heads, but again, like the book actually talks about making like a, two columns of like, here's the things you're given, here's the thing that's the thing you want to prove, which can be helpful. So we're given that n is even, and then we're given that there's this k, and n equals 2k. And then our goal now is to prove that n squared is even. How do we prove that n squared is even? Well, again, the definition of something being even means there exists some integer such that it's equal to that 2 times that integer. So if we can show that n squared is equal to 2 times something, right, the way we prove it exists is by actually giving an example and saying, here it is, this is the k that works, right? So what I can say is then n squared is equal to 2k squared, which is equal to 4k squared, which is equal to 2 times 2k squared. If we want to be really explicit about it, right? So the point is, since n squared is equal to 2 times an integer, it is even. Okay? Now let's prove that if n squared is even, then n is even. Any ideas or thoughts how we might approach doing this one? Sure.
Whatever we end up like writing in squared as has to be like
No? Okay. All right. Matthew?
I guess we did a contrapositive.
Okay, you want to do contrapositive? Yeah, so I agree. And again, you can either just try them both and realize that doing a direct proof, you're probably gonna get a little stuck. Contrapositive turns out it's gonna work better. Intuitively, you know, it's like, well, if we do the contrapositive, that means we get to assume something about n, and we have to prove something about n squared. And that seems like that's going to be easier, because kind of assuming something about something simple and using it to prove something about something more complicated is much easier than like being given something about something complicated and trying to use it. But again, I mean, like, you could just try both and see, you know, figure out what works. So let's say by contrapositive. So suppose n is odd, that is n equals 2k plus 1 for some integer k. Right, then we have to show that n squared is also odd. Then it's going to be the same kind of thing. N squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is 2 times 2k squared plus 2k plus 1. So n squared is odd. Okay, I left out a bunch of steps. You can, you know, of course, you could be more or less explicit if you want. Let's see. Let's do. For all sets A, B, and C, A intersect B difference C is equal to A intersect B difference C. All right, so we can start by saying, you know, let A, B, C be arbitrary sets. But what does it mean for sets to be equal, or how do I show that sets are equal? I think the way that we defined it is we said that each one is a subset of the other. Right? So we will show that a subset of the other?
It contains elements of that main set, but not all of the elements of that set.
It could be all of them, right? Subset, like a set is a subset of itself,
Okay.
right? But yes, you're right. It contains, like this set contains elements from this set. What's a different way of saying that might be more directly something that we could work with? Jason?
It doesn't contain any elements that aren't a part of the other set.
Okay, say that as a contrapositive.
It only contains elements that are part of the
Right.
other set.
Yeah. So I would say every element in this set is an element of this set. So that is, again, I'm going to write this out explicitly. You wouldn't have to write this. By definition of subset, we will show that for all x, if x is an element of A intersects B, oh, I'm missing parentheses here. Oh, I see. That one should be there, okay. If x is an element of A intersects B different C, that implies that x is an element of A intersects B different C. Okay, and this is something that, I mean, especially with like definitions involving set theory and stuff, you often start by, stating something, and then you're like, okay, well, wait, what is the definition of that thing? Well, let me like unfold the definition, or like replace the definition, replace something by its definition, and that like shows me how to proceed, right? Because if I just looked at this, by itself, and like, how do I prove that? Like, I don't know, maybe I like draw a picture of A, B, and C, and like kind of wave my hands and say, look, see, look at the picture. You say, no, okay, what is the definition? Well, the definition is, it's a for all. It's for all x. If x is in this, then x is in that. Okay, well, we know how to prove for alls and implications, right? So now we can make some progress. So let x be arbitrary. I'm playing a little fast and loose here because usually with a for all we have to say like, what domain is x from. It kind of depends on what domain the sets are from, and it doesn't really say that. It turns out it doesn't really matter in this case because whatever domain it is, the same proof will work. So, so let x be an arbitrary what? I don't know. It doesn't matter. An arbitrary thing. And suppose x is an element of A intersect B. Okay, I'm supposing this, and then I'm going to show this. Well, what does this mean? So now we can unfold definitions some more, right? And actually, I'm going to do it this way, just as an example of. I could just keep writing a paragraph, but I think this is going to be a helpful way to organize this. So I can say, all right, this is what I'm given, right? That implies, by the definition of intersection. Okay, so I think you've seen me do this kind of format before, where you like have some kind of expression or statement, and then on the line in between the next one, you'll have some kind of relationship. It could be like we've seen like equals, right? But it could be implies, or it could be if and only if. It could be is a subset of some kind of relationship to the next line, and then on the same line you put like the reason why that relationship holds, right? So by definition of intersection, well, you tell me what is the definition of if x is an element of A intersect B different C? What does that mean? something is in the intersection if it's in both of them. So I can say that implies X is an element of A, and X is an element of B different C. Okay, well, this implies X is an element of A, and what does this mean? If X is an element of B different C, what does that mean? So this is by the definition of difference. What again?
X is an element of whatever is in B but not in C.
Right. X is an element of B. Yeah, and we say but not, the word but actually just translates to and, right? You know, I would definitely say it with the word but in English, but, okay. Right? And now, and remember what my goal is, right? My goal is to show that X is an element of A intersect B different C. And so, another thing I could do is I could maybe start from the other side and be like, okay, well, what does that mean? But I can actually see that really what I want to do is I can appeal to the fact that and is associative. I can say, you know what, I can regroup this a different way. Okay, so this is the definition, or no, it's not definition, sorry. And is associative. Okay, that's one of the properties that we learned about and. And now, I mean, okay, I could do multiple steps, but I can just see at this point, look, this is the definition of X being in the intersection of A and B. And then, you know, this means, and it's not in C means we're taking a difference of C, right? So this is saying X is an element of A intersect B different C. So this is by definition of intersection. Okay, it's fine. And, you know, you could write this out in paragraph form, saying like, well, since X is an element of A intersects B different C, you know, that means that both X is an A and X is an B. Well, you could just write out all the steps. And there's nothing wrong with that, but sometimes I think, especially when it's just we're just going to be applying a bunch of definitions, you can do it in a sort of, I would call this like a calculational style, where you alternate each line, so you're alternating between writing down some kind of expression, and then the alternate lines have, you know, how those two things are related and the reason for why that relationship holds. And typically, the relationship that we use, as long as this relationship is transitive, that means you know, if this is related to this and this is related to this, that means this is related to this. Right? Any kind of relationship that's transitive, you can make a big chain of reasoning like this. So it works for equals, it works for implies, it works for is a subset of, it works for if and only if, it works for logically equivalent to. I mean, there's a ton of relationships that we like to use in math that are all transitive, and you can use this same kind of style doing this. Kind of a little aside, but cool. Any questions about this one?
Just a comment, I think this one makes the most sense out of all the ones we've done.
Okay.
I think maybe it's just because we've done some examples in previous modules where we're doing that chain,
Right.
especially in module
Yeah,
1.
exactly. Yeah, so maybe if you only take one thing away from today, I hope you take more than one thing away, but if you only take one thing, thinking about having this as a tool that you can use, this kind of format can be really helpful in organizing, right? Because I see often you know, you just end up kind of like writing down kind of a sequence of equations or things, and it's like, it's not even clear what's the relationship between them, and you can get yourself confused pretty easily that way. So even if you like have an equation and you're trying to solve it, right, you could use this same format where you say like, you know, x plus 3 equals 5y, if and only if, you know, x minus 5y equals, right? So you can even have an equation that's related to some other equation through like, you know, an if and implies or an if and only if. And like your sequence of steps, you're saying like, well, if this equation holds, that's true if and only if this other equation holds, because I like did the same thing to both sides. That's true if and only if this holds, right? That's really what you're doing when you're solving an equation. And you're doing the same kind of sequence of reasoning, and you're getting from the original equation down to like, you know, x equals 19 or whatever. And you're like, well, look, x equals 19 if and only if, through this big chain of reasoning, that original thing, so therefore that's the solution. So I would encourage you to think about using that format when you're writing, I mean, any kind of reasoning or proof or solution to something. All right, I think we're out of time. There's a couple other examples I had. Maybe we'll do a few more examples on Monday, but I'll see. Cool. Have a good weekend, y'all.